today I'm gonna be making the chapter 7 course, like the notes PDF for the periodic. So let's start. Chapter 7, it's about the electrons on the periodic table. So they're telling us, recall that the three subatomic particles, you have to remember the three subatomic particles: protons, neutrons, and electrons. Recall the atomic and proton number, that it's the atomic number is the amount of protons in an atom, and that the mass is the amount of protons and neutrons in an atom, and that the isotopes of an atom are they have the exact same atomic number, electron number, yet different neutron number. So, and you need to recall how to find the average atomic mass using isotopes, masses, and percentage abundance. If you don't, this question is gonna remind you. So the element copper has two natural occurring isotopes of mass number 73 and 65. The relative abundance is in this ratio. Calculate the average atomic mass. So what you need to do is you take the isotope mass, multiply it by the percentage, how much it is. So 63 has a 69.2%, and 65 has a 30.8%. When you add these two numbers up, you should get them equal to 100. Yeah? So this is how much percentage each one is in your molecule. 69.2 and 30.8. So you do 69.2 times 63, which is the atomic mass for this isotope, and the percentage 30.8 times the atomic mass of the second isotope, and you divide that by the 100, because when you add these two numbers together you get 100. So you add them up, and when you put all of this in your calculator, you're gonna get that the average atomic mass of copper is 63.6. And another way, if you want to check your answers, you can always look at your periodic table. I'm trying to find copper on mine, but wait, I'll find it. Yeah, so on your periodic table, I found it. It's element 29, and if you can see on your periodic table, it says 63.546. So it's relatively close to 63.6. So that's how you find it. So if you want to double check, always check your periodic table, because here the percentage yields they gave you are accurate, but not that accurate. That's why you got not the exact decimal point. But anyways, an atom consists of a central design. So how do you draw an atom? You have your nucleus, which is the dense region where you can find protons and neutrons on it. Protons are positive charged and neutrons are neutral. They have no charge. And all this nucleus is surrounded by electrons. So here you're gonna find electrons. The electrons are found on this thing called an electron cloud. So you can define, so it's telling you here in the next point that an atom consists, that the area around the nucleus where electrons have a high probability of being found is defined by shell numbers or energy levels. As the shell's distance away from the nucleus increases, its energy increases. So if your nucleus is here, and you have a shell here and a shell, let's say here, this shell, the one I just drew on, will have a higher energy than this shell, because when you increase the distance, energy also will increase. Now, another thing is that electronic configurations can be written in many ways. Simplest way is to do it in the way like I personally prefer to do it. There's like two ways that we know of now for this grade. So writing it as the 2, 8, 8, 2, let's say, this is calcium, 20. So how do you write it? Always for your first number, you write 2. If it's like, let's say it's element 14, silicon. Silicon is element 14, Si 14. It has an atomic number of 14. So to write its electronic configuration, you first start with the first shell. If you look at silicon on the periodic table, it is the third row. A row is the horizontal and the column is the vertical, or it's called the group. and the rows are called periods. So it is on the third row, so it should have 3 digits in it for silicon. First digit always is gonna be 2. You cannot have more than 2 on your first digit. So on your second digit, you'll do 14 minus 2. You're gonna get 12. But another thing, any shell after 2 cannot hold more than 8. The next shell can only hold 8. So what do? 12 minus 8. You're gonna write 8 here, and then you do 12 minus 8. How much are you left with? 4. Now when you add them up, they should equal 14. So 2 plus 8 is 10, 10 plus 4 is 14. And that's how you write the electronic configuration of silicon. And by the way, it turns out it's here. Now, here, they're asking us to write electronic configurations. Now, in the CQDs, if you look at the answer sheet, they write almost every single one in the SPD method, which is the method that I did here. But our teacher told us this thing. Most likely, they will never, ever specify in what way should you write your electronic configuration. If they do not specify how to write your electronic configuration, don't even think about this. Act like it doesn't exist. Write it in this way. It's way easier. It's more guaranteed. You can't mess it up. The computer isn't gonna take it as a wrong answer. And you don't have to waste time writing the exponents and whatever for this method. But I'm gonna show you both. For NA, it's 11. So we said first shell 2, second shell 8, last shell is the 10. 11 minus 10, which is 1. Then P15, same thing as the one in the silicon I showed you. 2, 8, that's 10, 5. And then for K, it's 19. So we said any shell after the 2 can hold up to 8. So 2 for your first shell. Then you can hold an 8, that makes 10. Then you can hold another 8, which makes 18. But you need 19, so you add an extra 1. And if you look at your periodic table, K is on the 4th row, meaning it has 4 energy levels. Now, let's say they specified, which most likely they won't, but in case they specified that they want NA written in SPD electronic configuration. What do? You write, for your first energy level, it's gonna be called, what's it called? S. So, 1. Then you write S power 1. Then 2. S power 2. Okay? So, wait guys, I think I made a mistake when writing it down. This should be 1S2. There's no such thing as 1S1. So look, it's for this electronic configuration, you start off with shell number 1. We said it can only hold 2, so you write 1S2. That's your first shell. That's like the substitute the first number. Now for your second shell, you're gonna write 2S2 because we're gonna act like the shell is made of shells. And then 2P6. What does this mean? It means that the second number 8 can be made of, this is energy level 2, which means it's the second number in the electronic configuration. So you can make it by filling up one full 2 and then 2P6. When you add these two numbers together, you're gonna get the 8. So that's your second number. So 1S2 and 2P6, yeah. That's how you write your second energy level. Now for your third one, so 1S2 is your first number. 2S2P6 is your second number. Now for the third shell, you write 3S1 because you have only 1 and that's it. So 1 stands for what period it's in, the 1, 2, and 3. So 1 can be in period 1, 2 is in energy level 1, 2 is energy level 2, 3 is energy level 3. So that's how you write it. So 1S2 substitutes for the 2, 2S2 2P6 substitutes for the 8, 3S1 substitutes for the 1. If you want, let me try writing the electronic configuration for the second number. So here you have 285. So we're gonna start off 2S2. Now for the 8 again, 2S2 2P6. Now for the 5, 3s5. Or wait, no, not 3s5. It's 3s2, 3s3. That's how you draw it. See what I mean with this way? It's really confusing to draw, and like you personally, I don't think any student has the brain power to do this way in the exam, especially if we have the option to do it in this way. So don't do this way ever unless they specifically ask in SPD method. If they don't do it. Now, for the next thing, it's the exact same thing, right? Electronic configurations of Li3 and P15. 3 and P15, I did it already above. It's the exact same thing. For question 8, exact same thing, except here they told us use the 288 configuration. So you have to write it in this way. If they don't mention how to write it in this way, please. Because that was almost guaranteed to get you a mistake. And especially when we don't have time in our periodics. Now, the periodic table is arranged in periods, horizontal rows, groups, vertical rows, and blocks, which are the elements. Periods are horizontal, groups are vertical, and the period which you can find it in tells you how many shells it has. So if it's in period 3, it has shell 1 of electrons, shell 2 of electrons, and shell 3 of electrons. Sorry for my lines. That's what they're telling you here. Hydrogen and helium are the only two elements in periodic 1 because they have electronics in the first shell only, H1 and He2, because this is how you draw their elements. You draw your nucleus. I'm gonna write H instead of the nucleus, and their electrons are 1, and for He 1, 2. That's it. You don't need more than one energy level, because the maximum you can hold in the first energy level either way is 2. Now, an element whose electronic configuration is 281 belongs to period 3. Why? Because 281. Because it has 3 shells. Now, groups are the vertical rows. You can find from the group the number of valence electrons. So if you have 284, it means that it has 4 valence electrons, which means it is in group 4. And that's how you find it. Now, for core electrons, the inner shell electrons that are strongly bound to the nucleus. So what that means that is if you have 2 and 5, the electronic configuration of nitrogen, the number of valence electrons is 5 and the number of core electrons is 2. Now, the electronic configuration of noble gases always ends in 8. If it doesn't end with 8, unless it is He, it is not a noble gas. He is the only one that does not end with 8 because it only has 2 electrons. And we know that all the elements are trying to be like noble gases. So they either give away their electrons, they take electrons from other elements, or they share electrons, and so on. Now, they're always inert. You say they're inert because they're unreactive and their outer shell is full. They don't need anything more. So they exist as monoatomic gases. They do not combine, they do not mix, they do not share, they do not give or nor take from other elements. Other elements will tend to gain, lose, share to achieve the same electronic configuration as the noble gases. Groups 1, 2, and 3 will lose electrons. Metals in group 1, 2, 3 will lose electrons. Group 1 will lose 1. Group 2 will lose 2, and group 3 will lose 3. Mg loses 2 electrons, so they become positive when you write it. So Mg loses 2 electrons to become 2 plus. Okay? Group 5, 6, and 7 will gain electrons. Group 5 will gain 3 electrons, group 6 will gain 2, and group 7 will gain 1 electron. So group 5 elements will all be, let's take an example, N3 plus. N3 minus, because they lose 3. They gain 3, so they become minus. When they lose, they become positive, because you have more protons than electrons. Yeah, so they want to reach the highest electronic configuration of the nearest noble gas. So O8 has 2 electrons and less than neon, so it will share 2 to get the configuration like neon. Now, group 4 elements, they don't gain nor they lose. They always share. Now, isotopes of the same elements have the same chemical properties because they're the same element. They have the same number of protons and electrons, but they have an imbalance in their nucleus. So they're telling us here that isotopes, they act the exact same way as the elements themselves, but since their nucleus is unstable, they spontaneously break up and emit radiations. We took this in physics. So isotopes are called radioactive. Carbon-14 and tritium are two examples. You can use them as energy sources. That's number one. You can use them as tracers. That's number two. Like you can see where the flow of a substance is in the human's body. So yeah, they use radioactive iodine to find out if a patient's kidney is blocked. That's one use. And they use it for dating, to find out how old a material is. Like when you want to find out how old is this tree, you can use carbon dating to find out. Yeah, it's usually you use carbon or uranium isotopes for carbon dating, or dating in general. Elements in the same group they are similar. They have similar properties because they have similar valence electrons. The same valence electrons, not similar. That's why when you look at the element in the periodic table, its row will tell you how many energy levels you have, and its group is going to tell you how they act, how much valence electrons they have, who are the ones like them, and so on. So what's so special about the electronic configuration of noble gases? They have full shells, all of them. Is this the noble configuration of a noble gas? If it ends with 7, then no, it is not. Now, moving on. Here they want us to fill in the electronic number of electrons on each energy level. So Li to 1, so it's in period 2 because it has 2 digits. Number of valence electrons is 1, and it means it's in group 1. This number and this number, these two numbers are always going to be the same. So K19, it's 2881, so it's in period 4 because you have 1, 2, 3, and 4. And it ends with 1, so it's in group, it has 1 valence electrons, so it's in group 1. Now 285, so it's in period 3 because it has 3 numbers, and number of valence electrons is the 5, so it's in group 5. Here argon is a noble gas, so 288, it's in period 1, 2, 3, so it's 3, and its last number is 8, so it's making it in group 8. Now ions are the charged species formed by losing or gaining electrons. If you lose electrons, you become a cation, which is the positive. So if you lose, you gain the positive sign. But if you gain, you get the negative sign, because electrons are a negative thing. If you lose them, you become positive. If you gain them, you're more negative. So when you gain 1 electron, you become +1, or 1 plus, as they write it. The number of protons is greater than the number of electrons if you have a cation, and metals are always the ones to form the cations, or they tend to form. And if it's an anion, they gain 1 or more electrons. They become negative. Their electrons are more than their protons, and usually these are found in non-metals, and negative ions are called anions. Now, electronic configuration of ions can be written only after determining the number of electrons in the ion. Cation, consider the number of atomic number in the atom and subtract it from the cation's charge. So if you have 13 electrons and it is 3 plus, you minus 3. And if you have an anion, like let's say Cl minus, Cl usually it has 17 electrons because its atomic number is 17. If it's Cl minus, you will have 18 electrons because you take the -1 and you add it to this number. Add it. Cation, you take the number and subtract it. So Al 3 plus has 13 electrons. So if it's 3 plus, you minus 3. If it's F 1 minus, so 9, and then you add 1. So 28, 28. And always, if you want to check if you wrote the ions atomic electronic configuration right, you look at the noble gases. If it matches any of the noble gases, then your answer is correct. If it does not match a noble gas, you did something wrong along the way. Now write the electronic configuration of the following ions. O has 8. If it's 2 minus, you do 2 plus. So 8 plus 2 is 10. And 10 is 2 and 8. Na, same thing. You had 11 and you have plus, so you minus 1. Also giving you 10, so 2, 8. Mg 2 plus, so you have 12. 2 plus means you minus 2. You're gonna get, you figured it out, 10, which is also 2, 8. Now, N3, same thing, 7 and minus 3 make, you add 3 and becomes 10, 2, 8. All the examples here, they made them that they look like neon. Now for this question. This question is actually really easy. You just have to know the how many electrons each element gains or loses. So barium oxide. Barium is in group 2. Oxide is in group oxide means oxygen, so it's in group 6. So barium in group 2, this is the number of group, and oxygen in group 6. We know that barium will gain 2 electrons and that oxygen in group 6 is gonna lose barium is gonna lose 2 electrons and oxygen is gonna gain 2 electrons. So now oxygen gains 2 and barium loses 2. So if they're the same number, just write BaO. If they're the same. Now, but for boron is in group 3. So it is 3 plus. Oxygen is in group 2. So it is 2 minus. What do you do in this case? You give the 2 to the B and the 3 to the O. You're gonna get B2O3. And that's how you write it. For aluminium, it's a transition metal, but no, it's aluminium 3 plus. And we know that F is 1 minus. So what do? You give the 1 to the Al and the 3 to the F. But when you give 1 to any element, you don't write the 1 down. So Al, F, 3. That's how you solve. Let me solve the rest. Sodium sulfide, sodium Na plus 1. And sulfide S2 minus. So you're gonna get Na2 S bus. Because S1, but you don't write the 1 if it's 1. Calcium nitride, Ca2 plus N3 minus. They're different, so you cross. So you're gonna get Ca3 N2, and that's how you do it. I think you're getting the picture, but it's the last example for this. Let me do it really quick, and then we'll move on to the ions themselves. So potassium oxide, K plus 1, O2 minus, switch becomes K2O. And that's it for all of the molecules. Now chloride ion, chloride's in group 7, so it becomes Cl minus. Barium chloride, I did enough of these examples. Ba2 plus, Cl minus, switch. Aluminium, Al3 plus, N3 minus, so it's the same, so you don't write any of the charges. If they're the same, you don't write them. Aluminium ion, Al3 plus, sulfide ion, S2 minus, and nitride is N3 minus. How do you find these? You look on the periodic table. Sulfide is in group 6, so it will lose 2, so it will gain 2, so it will become 2 minus. Nitride in group 5, so it will gain 3, so it will become 3 minus. Phosphide, same thing as nitride in group 5, so it will gain 3, so it will become 3 minus. Calcium is in group 2, so it will lose 2 and become 2 plus. That's it for this table. Now here, they're showing us these 3 particles, A, B, and C. And they told us that the green is the electrons, the blue is the protons, and the pink is the neutrons. And they're asking us, particle C is a negative ion. Why? So particle C has 8 protons, but let's count how many electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if it is 10 electrons and 8 protons, it has more electrons than protons. What did we say it happens when you have more electrons than protons? It's a negative ion. That's why. Because they have more electrons than protons. Now A, B, and C are particles of the same element. How do you know if they're from the same element? You look at the number of protons. If they have all equal number of protons, then they are all the same element. Protons is what determines what element they are. And A and B are isotopes of the same element. Why? Because they have same number of protons, same number of electrons. They both have 8 electrons, as you can see here. But they have different numbers of neutrons. So we said same electrons, same protons, different neutrons means they're isotopes. Because they all have the same number of protons. A and B are isotopes because B has one more neutron but equal number of protons and electrons. Now, A is a nonmetal. Why? We know A is a nonmetal because it has 8 protons, meaning it's in group 6. If it has 8 protons, so it has the tendency to lose it has the tendency to lose electrons to form negative ions. So, yeah. Did I say lose? Because it has the tendency to gain electrons to form negative ions, because it doesn't have a full final shell. If it had a full shell, like here, then it wouldn't, be... What's it called? It wouldn't, be a non-metal. Because see, here it only has 6 electrons. To reach 8, or to reach noble gas configuration, you need 8. So it has 6. Counting these, of course. Not counting these. Counting these, you have 8. But you need your final shell to have 8. So it has to gain 2 to become 8. So it's a non-metal. Now, how do you identify A? And write its symbol. So you look at the number of protons, you look at your periodic table. O has the number of protons 8, or the atomic number 8, so it's O. You write number of protons down, 8, and number of nucleons up, or the mass number up, 16. Now, if you wanted to write the atomic number for particle C, which is the same element as A, but with the ion, it's the ion of it, you write O. 8 will never change. 16 will never change, but now it's 2 minus. Why? Because it gained 2 electrons here. It has 8 on its final shell here. It's supposed to have, the original one had 6. This has 8 on its final. So it's 8, what happened? You gained 2. So 2 minus. Now, an atom has 16 electrons. What's the electronic structure of X? So if it has 16, 2 is the first energy level, 8 is your second, then 2 plus 8 is 10, 16 minus 10, 6 is your third. And that's it for chapter 7. These are all the CQDs in the notes, and most likely all the CQDs you need to know. And that's the entire chapter. It's really easy. If you remember, if you were focusing in your previous years in chem, you would probably already know all of this information. We didn't really add anything new. Other than this, some students might say we never learned it before, even though we kind of did, but not all schools actually focused on it. And yeah, have a good day. Bye.